So taking a look at that sapling question, this is an interesting one. It asks you to think about a lot of things. Asks you to think about aldehydes versus ketones as far as reactivity goes. It asks you to think about carbon stability as far as ring size goes. Right? What are the size rings carbon likes to form? And then there's some enolate chemistry, and you do some cyclizations. And if there's some heat around, which I think there was in this, right, that should be a tip-off, right? When you see heat, you can think about not just an Aldol type reaction, that's what this is going to be, but you can also think about condensations, which leads to conjugation. So first, let's number our carbons. 1, 2, 3, 4, 5, 6. Ask ourselves which carbons have alpha CHs that are acidic, right? How do I know that? Again, we're going back. Well, OH minus is a strong base, and aldehydes and ketones, right? They don't have good leaving groups, so even if the OH minus adds, there's really no OH minus is still the best leaving group. So they're going to be more prone to do enolate formation, acid-base chemistry, deprotonation. So which carbons have alpha CHs? 2 and 4, right? 5 doesn't, right? There's 2 methyls there. So 5 does not. So now the question is, okay, if I make an enolate here at carbon 2, so I put a negative charge there, what's it going to react with? So this is going to be the ketone side of this molecule is going to be my nucleophile, which means my aldehyde left over here is going to be my electrophile, because an intramolecular reaction is more likely to take place than an inter, right? Molecule can react within itself faster than it could with whole another molecule someplace else. So that means this side is going to be my nucleophile, and this side will be my electrophile. So we need to ask ourselves, okay, if carbon 2 is a nucleophile or carbon 4 is a nucleophile, what would happen if they reacted with carbon 6? We know for sure carbon 6 is the electrophilic carbon. The question is carbon 4 going to be the nucleophile, or is carbon 2 going to be the nucleophile? So let's look at, so if carbon 2 is a nucleophile, it would form with carbon 6, so it would be a 1, 2, 3, 4, 5-membered ring you'd form. Because we're going to form a ring, right, because it's in the same molecule. If it's carbon 4 reacting with carbon 6, you'd have a 1, 2, 3 carbon ring. What do you think is more likely, 5 or 6 carbon, 5 or 3 carbon ring? 5, right? So 6 is the best, like chair conformations. 5 is next best, right? So that's what we're going to do. We're going to deprotonate here, make an enolate, deprot. All right, so carbon 2 is our nucleophile. Right? I just drew it in the enolate form. So carbon 2 still is our alpha carbon, still the nucleophilic carbon. It's not oxygen. Electrons come down. Pi bond attacks carbon 6. We're doing an addition reaction here, right? An addition reaction. Making a tetrahedral intermediate. So I can draw this pretty, or I want to draw it ugly first? Let's draw it ugly first. One, 2, 3, 4, 5, 6. So there's certainly the ugly version. Made a 5-member ring. I can redraw it. I would just draw the 5-member ring first. I know the bond I formed was between 2 and 6. 6 was bonded to 5, which is bonded to 4, which is bonded to 3. Carbon 1 is bonded to 2. Carbon 3 has a carbonyl, and carbon 5 has 2 methyls, and now carbon 6 has an O minus. There you go. All right, then the next step, that a water that we originally made from that first step, the O minus is going to take that H. We're going to regenerate OH minus. So a deprotonation. And that's going to make that traditional aldol product. I'm going to bring my carbons. That was a 1, 2, 6, 5, 4, 3. That's that aldol product, right? The alcohol. But notice at the beginning, right, we have heat. Remember, be careful about your temperatures. That matters. You can decarboxylate. You can do these condensations if there's heat around. So that's what this is going to do. And where's it going to, what kind of reaction is it going to do? It's going to do actually an E2 reaction. It's going to do a aldol condensation, right? Because that alpha hydrogen that's still there is pretty acidic. And we can actually just do an E2 reaction regenerating OH minus. So that's an E2. And that gives us the aldol condensation product. It's ugly. Try again. OH minus. Again, we made water. Number those carbons. 1, 2, 6, 5, 4, 3. There you go. Aldol condensation because of the heat. That's that last step, that E2 step. Point to bring attention. OH minus is not a good leaving group, right? How are you doing this E2 reaction if OH minus is not a good leaving group? Well, you're starting with OH minus, right? So there's OH minus in the system. And that also comes back to that energy. It's going to take a lot of energy to make this go, because OH minus is actually not a very good leaving group. So that's part of the reason why you need that heat. But you also have OH minus around too, so it helps. It's a good enough base, but yeah, OH minus is a bad leaving group, absolutely. But you're making something that's conjugated, right? Water's a byproduct. You could dehydrate it, right? Things you could do to force it towards this way, and then the heat really helps.